In this video, we're going to graph two of the basic trig functions. We're going to graph sine and cosine and look at the domain and range of sine and cosine. First of all, let's go back to graphing something we're more familiar with. For instance, a linear function. Let's take y equals 2x plus 2. We would come up with an xy chart, and for instance, if I plugged in x is equal to 0, y would be, let's see, 2 times 0 plus 2, that would be 2, and that would lead to the point 0, 2. And I've graphed it on the screen. Let's do another point. Let's do 1. If x is equal to 1, then y, 2 times 1 plus 2, y is equal to 4. And that leads to the point 1, 4. And again, I've graphed that. Finally, let's look at negative 1. Well, if I have x is equal to negative 1, that leads to y equaling negative 2 plus 2, or 0. Again, I can graph that point and connect the line, and I have graphed my linear function. And a little bit of review, we also can talk about the domain and the range of a function. Remember, the domain are all the possible input values you can have, and the range are all the possible outputs this function can have. My inputs are x, and there's no limit on my inputs. I can have any number from negative infinity to positive infinity. I've written this, by the way, in interval form. The range is the same way. There is no limit on my range. There's no limit on what my y value can be. So the range for this function is negative infinity, infinity. Alright, let's go and graph quadratic functions. We'll say y equals x squared. Actually, I'm going to be fancier than that. I'm going to actually put this in function notation. F of x is equal to x squared. So our input is x, and our output, f of x, is y. This should all hopefully be review. If x is 0, y is 0. If x is 1 or negative 1, the output is 1. And if x is 2 or negative 2, the output is 4. And those points connected together give me a quadratic function. It's a parabola. Now the domain for this one, again, there's no limit on what I can put in as an x for this function. However, no matter what I do, no matter what x I choose, I can't have a negative value of y. So my range is the point 0 up to positive infinity. Notice I've used a bracket next to the 0. That means you can actually equal the point 0 in my range, but you can never get to infinity, so we use a parentheses for the endpoint. Alright, well, let's look at graphing sine functions. I'm again going to be using Trig Explorer. Again, this is a software package available at www.mathrealm.com. Before I do that, though, let's go back to that table of trig values we talked about, I think back in video 5. If I have an angle of 30 degrees, 45 degrees, or 60 degrees, since we're looking at sine first, we've found that the sine of those values were 1/2 square root of 2 over 2 and square root of 3 over 2. Well, if I'm going to be graphing these, I really want to approximate them so I can put them on my graph. I don't know how really to graph square root of 2 over 2, so I'll use the approximations when it comes to graphing this on a xy axis. I also want to remind you that we have the unit circle that we've gone over, and on this unit circle not only do I have my different angles, but remember in part 2 of the unit circle video we talked about how we could fill in the x and y values. And remember, sine, back to that right triangle, was equal to y over the radius, or in the case of a unit circle, y over 1, or y. Cosine was equal to the x value, and tangent was equal to y divided by x. We'll be using this in graphing all three of these functions. Let's start off at 0 degrees, and I'm starting to graph this in degrees. I could have done this as easily in radians. In fact, we will before we're done. But at 0 degrees, if sine is equal to y, at 0 degrees on this unit circle, well, y is equal to 0. So sine starts off at the number 0. At 30 degrees, what was sine of 30 degrees? I think that was equal to 0.5. Let's see, it's a point right about there. So at 30 degrees, sine is equal to 1/2. If we go up to 45 degrees, remember the sine of 45 degrees was equal to, or approximately equal to, about 0.7. So I'm expecting, yeah, that looks like it's about 45 degrees, halfway between my 0 degrees and 90 degrees. If I kept going to my 60 degrees, I had 0.86, and all the way up here at 90 degrees, well, let's see, the y value at 90 degrees is equal to 1. So my sine, if my sine is equal to y, at that point, sine is equal to 1. Well, now we're done with the first quadrant. What happens when we spin this back to the second quadrant? Let's go to 45 degrees. Well, that's not really 45 degrees, is it? It's actually 135 degrees. Remember, an angle of 135 degrees has a reference angle of 45 degrees. Now, in quadrant 2, sine was positive. So I would expect sine of 135 degrees to be equal to sine of 45 degrees. And it is. Here we see this is about equal to 0.7 again on my graph. And I'll continue going down until at 180 degrees, well, let's see, at 180 degrees, y is again equal to 0, which we see on our graph. This is the point at 180 degrees, sine is equal to 0. Now if I keep going, say I go to 45 degrees in quadrant 3, that's still equal or approximately equal to 7/10, but remember in quadrant 3 sine is negative. So instead of 7/10, it's negative 7/10. Alright, and if we keep going down to 270 degrees, y at this point is equal to negative 1. And again going up to 315 degrees, that is again equal to 7/10, but we have a negative 7/10 because quadrant 4 sine is negative. And back up to 360 degrees, y is back equal to 0, so we cross again at 0. If I deal in terms of radians, then at sine of 0 radians, well, y is still equal to 0. Instead of 45 degrees, we would be talking about pi divided by 4, and we would still be equal to 7/10. At what we called before 90 degrees, well, that's just pi over 2, and again, sine of pi over 2 is equal to positive 1. The shape of this doesn't change. All we're doing is changing the measure that we're giving our angle in. If we look at the graph of sine of theta overall, we see that it starts at 0. It goes to a maximum of 1 at 90 degrees, or pi over 2, and it has a minimum at negative 1 at 3 pi over 2, or 270 degrees, and when it goes back up to 360 degrees, or 2 pi, it's back where it started. It also intercepts the x-axis at pi at 180 degrees. Let's now look at cosine of theta. Remember, cosine of theta is equal to the x value of the point xy. Well, the x value at 0 degrees is actually equal to 1. So whereas the sine started at 0, the cosine actually starts at the value 1. At 45 degrees, cosine and sine are actually equal to each other. Cosine of 45 degrees is also equal to 7/10. So we'll go ahead and stop there and say, yes, at 45 degrees, it looks like we're about at 7/10. What happens when I go to 90 degrees? Well, at 90 degrees, my x value is 0. So the cosine function crosses the x-axis at 90 degrees. Here I am at 45 degrees. Well, no, not 45 degrees. It's really 135 degrees, an angle with a reference angle of 45 degrees. But remember, in quadrant 2, cosine is negative, and you can see this on the graph. We have at about 135 degrees a negative 7/10. If I keep going, at this point at 180 degrees, x is equal to negative 1, and we see that on the graph. In quadrant 3, cosine is still negative, so at the reference angle of 45 degrees, in quadrant 3, we are still equal to negative 7/10. Here we are at 270 degrees. Again, the x value is equal to 0. But in quadrant 4, at a reference angle of 45 degrees, well, cosine is positive, so that'll equal a positive 7/10. and bringing us back to 360 degrees. Again, cosine of 360 degrees is positive 1. If I look at this in terms of radians, the only thing that changes is my markings on my x-axis. My scale is different. Instead of from 0 to 360 degrees, we're going from 0 to 2 pi. And let's look at the key points on the cosine function. Again, cosine starts at positive 1, whereas the sine started at 0. And it crosses the x-axis at pi over 2 and 3 pi over 2, or 90 degrees and 270 degrees. Its maximum and minimum are also 1 and negative 1, but they occur at different points. The maximum of 1 occurs at 0 degrees or 360 degrees, and the minimum, negative 1, occurs at pi or 180 degrees. If we recall, sine and cosine are cofunctions. That is, if I have sine of theta, that is equal to cosine of the complement of theta, or 90 degrees minus theta, or if we're talking radians, pi over 2 minus theta. And cosine of theta, because it's a cofunction of sine, would be equal to sine of the complement of theta, or sine of 90 degrees minus theta, or sine of pi over 2 minus theta. And if you look at the two graphs for sine and cosine, they look very, very much alike. They're just shifted by 90 degrees. For instance, if I look at, this is sine of theta, and if then on top of this I plot cosine of theta, then you see cosine of theta in blue is shaped exactly like the sine, but it's shifted 90 degrees. That's because the sine and the cosine are cofunctions. While we're at it, let's talk about the domain and range of the sine and cosine functions. Remember, the domain is the possible inputs, the possible x values. And quite frankly, I don't see any limit on our values of x. So the domain of both sine and cosine are negative infinity and positive infinity. The range, however, is limited. It can only go between negative 1 and positive 1. So that means the range for our sine and our cosine functions is negative 1 to positive 1. And because the sine and cosine can exactly equal negative 1 and positive 1, I've put the range in brackets, indicating that it can actually equal negative 1 or positive 1.